Measurements and uncertainties. There are 7 fundamental units that are used to represent measurements. The first is mass, and this can be written as kg, and this is kilograms. Second is length, this can be written as m, and this is meters. Third is time, this can be written as s, or the second. The fourth is electric current, this can be written as A and reads as amperes. The fifth is amount of substance, or the moles, and 1 mole is equal to 6.02 times by 10 to the power of 23 particles. And sixth is temperature, and this is written as K or kelvins, and 1 Kelvin is equal to negative 272.15 Celsius. And last is luminous intensity, which is written as CD or candela, but in IGCSE physics or IB physics, the understanding for this unit is not required. And using those fundamental units, there are some other measurements can be also derived. For example, force can be calculated using F equals to ma, and as the unit for m is in kilograms, and the unit for acceleration is meter per second squared, so the unit for the force would be meters per second squared. Next, for the speed, as the speed is distance over time, and the units for distance is in meters and unit for the time is in seconds, the unit for the speed would be meters per second. And in case of energy, this can be calculated using the equation E equals to half mv squared, and as the unit for m, which is the mass, would be in kilograms, and as the unit for the velocity would be meters per second, the final unit for the energy would be kilograms meter squared per second squared. And for the power, this can be calculated using the equation P equals to work over time, and as the work has the same unit for unit as the energy, the unit for the power would be just dividing the unit for energy by time, and this gives kilogram meter squared per second cubed. And significant figures are this indicates possible range of values for the quantity measured. For example, 24.234 grams has 5 significant figures, and it gives the range as plus or minus 0.001 grams. And in case of 24.2 grams, it has 3 significant figures, and it gives a range as plus or minus 0.1 grams. And there are 2 types of errors. First is random, and second is systematic. And the random error is caused because of the readability of the instrument, or the observer being less than perfect, or the effects of a change in the surroundings. And this can be reduced through repeating the experiment. The systematic error arises because there's an instrument with 0 error, and to correct for 0 error, the value should be subtracted from every reading. And instruments might be wrongly calibrated, or the observer might be less than perfect in the same way every measurement. Here, the word same way is quite important, because if the observer becomes less perfect in different ways in every measurement, it would be more like on random errors rather than systematic errors. And this cannot be reduced through repeating the experiment. And there are 2 important terms you need to know, which are precision and accuracy. Precision means how much the values are close to each other, and accuracy means how the values are close to the targeted value. So in the diagram 1, the values are close to each other, but it's far away from the targeted value, so it has high precision but low accuracy. The second diagram, the values are close to the targeted value, but the values itself are quite further apart to each other. So it has high accuracy but low precision. In the third diagram, the values are further apart to each other and it's far apart from the targeted value, meaning that it has low precision and low accuracy. The last diagram, the values are close to each other and the values are close to the targeted value, so it has high precision and high accuracy. Uncertainty calculation. There are three types of uncertainties, which are absolute, fractional, and percentage uncertainty. Absolute uncertainty can be written as plus or minus delta p, and fractional uncertainty can be written as plus or minus delta p over p, and percentage uncertainty would be plus or minus delta p over p times by 100%. The length of the pencil, and it can be 6.2 plus or minus 0.1 centimeters. Here the absolute uncertainty would be plus or minus 0.1, and the fractional uncertainty would be 0.1 divided by 6.2, and this gives 0.016. And percentage uncertainty would be multiplying 100% to the fractional uncertainty, and this gives 1.6%. Next is addition and subtraction of uncertainties. No matter adding or subtracting, the absolute uncertainty would always be added. So when calculating the equation y equals to a plus b, the uncertainty for y would be delta a plus delta b. So for example, the a can be 10.2 plus or minus 0.1 meters, and b can be 20.4 plus or minus 0.3 meters. And let's calculate the value c, which is a plus b. The uncertainty of c would be 0.1 plus 0.3, and this gives us 0.4. And this can be also written as delta c is equal to 0.4, and this gives us the final value for c, which is 30.6 plus or minus 0.4 meters. Next is multiplication and division of uncertainties. Here, no matter multiplying or dividing, the percentage or fractional uncertainty is always added. So when calculating y equals to a times b, this would be delta y over y equals to delta a over a plus delta b over b. So here the same values for a and b would be used, and this time the c would be a times b. So the delta c over c would be equal to delta a over a plus delta b over b. By subtracting values in, this would be 0.1 over 10.2 plus 0.3 over 20.4. And this gives us the final value of 0.0245. And this would be equal to delta c over c. And as the c would be multiplying 10.2 times 20.4, and this would be 208. Therefore, the delta c would be 0.0245 times by 208, because by multiplying c to the each side of the equation, and this gives us 5.10, and this would be the absolute uncertainty for the c value. So the final value we get for the c would be 208 plus or minus 5 centimeters squared. Okay, thank you.